Hi, this is Tom Tolbert, Pulmonary and Critical Care Fellow, and welcome to this lecture on the basics of mechanical ventilation. Here's what I'm going to talk about in this, just very briefly on respiratory mechanics. I have another video that goes into more detail on this, so I'm only going to touch on it briefly. I'm going to talk about the mechanical ventilator itself, what it looks like, and how you can identify the parts, the fundamental concept of who gets control of breathing, as well as the phase variables. During inspiration, there's a patient effort created by the diaphragm that overcomes the stiffness pressure of the lungs and chest wall, as well as the resistance pressure of the airway, in order to drive a tidal volume down into the lungs. The important thing about expiration is that it's passive. That is, the effort that is created by the diaphragm during inspiration stretches out the lungs and chest wall like they're a spring. And so when that effort goes away, what you're left with is recoil pressure from the lungs and chest wall. So they're stretched out, and the force of them retracting create a pressure that's enough to drive the tidal volume back out of the lungs and into the atmosphere. End expiration is still part of expiration, but it's special, and it's kind of sometimes considered like its own phase because there's no more forces acting to move air. The tidal volume has come out of the lungs. The lung and chest wall are no longer stretched out, so they're not exerting any recoil force. They're back to their starting phase. So there's no more stiffness pressure. And because there's no more flow of air, because there's no pressure to drive flow of air, there's also no more resistance pressure, because resistance is the pressure from resistance just comes from flow down the airway. If there's no flow down the airway, there's no resistance pressure. So all this stuff just disappears, it's just gone, and everything's static. Nothing's moving at end expiration. When you add a ventilator, there's only a couple changes to the mechanics here. The first is that instead of just having patient effort, you also have a pressure created by the ventilator, and that's the positive pressure. So patient effort creates a negative pressure, the ventilator creates a positive pressure. Both of them work together to drive a tidal volume into the lungs during inspiration and to stretch out the lungs and the chest wall. Just like during expiration when you're not mechanically ventilated, the force that drives the tidal volume back out of the lungs is due to the recoil pressure of the lungs and the chest wall. The ventilator and patient effort of the diaphragm have worked together to stretch the lungs and chest wall out like a spring, and when both of those things are gone, these are allowed to recoil just like a spring, to go from that stretched state back to the relaxed state, and that force is enough to move the tidal volume back out of the lungs. Apparently there were some old ventilators that actually sucked air back out of the lungs, but modern ventilators don't do that. Modern ventilators don't suck, they blow. So they only push air in, and it's always the lungs and the chest wall that relax to push the air back out. Just like end expiration when you're not mechanically ventilated, the chest wall recoil and lung recoil pressures have gone away because they've gone from their stretched out state back to their resting state. So there's no more stiffness pressure, there's no more resistance pressure because there's no movement of air, there's no flow, so there's nothing to create resistance pressure. So all this goes away. The difference with the mechanical ventilator is that you can give positive end expiratory pressure. That is, instead of exposing the airway to atmospheric pressure, you can put a positive pressure here, and that's called PEEP, or positive end expiratory pressure. And that has a lot of effects that I'm not really going to get into here, but that's the only other important difference between a not mechanically ventilated patient and a mechanically ventilated one. So nothing's moving here at end expiration, all flow is gone, tidal volume's out of the lungs, and you're applying PEEP. At my institution, the major mechanical ventilator we use is the Puritan Bennett 840 or the PB 840, and this is what it looks like. This is the whole apparatus with the screen and all the tubing and the wheels and everything. This is a patient, of course, as we've previously depicted, and this is the tubing between the mechanical ventilator and the endotracheal tube, which is in the patient. You can identify the separate parts by color. The inspiratory tubing is usually a dark blue, and you can also identify it by that it comes out of a humidifier, and this is the same humidifier that you'll often see on a high-flow nasal cannula setup. And so the air comes out of here, gets humidified, goes into the patient, and then during expiration, the air comes out of the patient and goes down the expiratory tubing. And the expiratory tubing is usually a lighter blue or almost like a white. And you can tell also by that it goes into a CO2 filter. If you look closely, it's like this round circular thing with a paper-looking, jagged paper-looking filter in it. So air comes out of the inspiratory tubing, goes into the patient during inspiration, and when it comes out of the patient, it goes down the expiratory tubing into a CO2 filter. So we went through the ventilatory cycle, and we talked about inspiration and expiration, and we said that expiration was passive, meaning it depends on the patient's own mechanics. The ventilator doesn't suck the air back out of them, it just lets the patient's chest wall and lungs relax to push the air back out. So a way to think about it is to say that a mechanical ventilator is a provider of inspiration, or it assists a patient with inspiration. Therefore, a fundamental question about mechanical ventilation is who gets to control that process, who gets to control breath timing. That is, when inspiration starts and when inspiration ends, because that's the ventilator's work. The ventilator's work is to provide inspiration, and it just needs some direction about when inspiration should start and how long it should last. The easy answer is you could just say that the ventilator gets complete control over when inspiration starts and when inspiration ends, meaning that you basically ignore whatever the patient is doing and let the ventilator's own CPU, the computer inside the ventilator, decide this is when I'm going to start giving inspiration and this is when I'm going to stop giving inspiration. On the other side, you could give the patient complete control over when inspiration starts and when inspiration ends, but there has to be some signal that travels from the patient to the ventilator to tell the ventilator this is when inspiration is, so this is when you need to provide the support, provide that pressure from the ventilator. Remember that the connection between the patient and the ventilator for most modern ventilators is only this tubing. There's no wires, there's no other way to give a signal between the patient and the ventilator. So the signal has to be either a pressure or a flow that comes from the patient having an inspiratory effort that the ventilator can detect in these tubes to say, okay, this is when the patient wants inspiration to happen. And that's how you give the patient control over when breath timing occurs. To summarize it again, you can either give the CPU complete control and you just ignore patient efforts, or you can use the changes in pressure and flow in the tubing that are caused by the patient's inspiratory efforts to tell the ventilator that this is when inspiration starts and this is when inspiration ends. In between the extremes of giving the vent complete control and the patient complete control, there's kind of a combo of both. Sometimes you have the vent completely controlling and sometimes you have the patient completely controlling, sort of depending on what's going on, what efforts the patient are making, and how high you want their respiratory rate to be. And that's where AC modes come in, assist control modes. They tend to be a combination of the vent has complete control over when inspiration happens and the patient has some control over when the inspiration happens. Here's a close-up look at the interface or monitor on a PB840 mechanical ventilator. It's got three different sections that pertain to what you actually set on the ventilator and then what actually happens during each respiratory cycle. So down here at these blue buttons are the actual vent settings. You can click each one of these and adjust them to whatever variables you want. Up here at the top is the actual output as measured by the ventilator. So for example, here you could set a tidal volume of 500, but what you're actually getting out, at least during the most current breath, is 519. In between the vent settings and the actual output are these graphs or curves, which are usually some variable over time, and the ones I like looking at the most are the pressure time and flow time curves, and this is just another way at looking at the output of each breath. And down here at the bottom are the inspiratory and expiratory pause buttons, which are important in a lot of clinical circumstances. When you're rotating through the ICU, I really encourage you to take a close look at the pressure time and flow time curves, because this is really how I learned basically everything I know about mechanical ventilation was by practicing and looking at these curves carefully, because these represent what the ventilator actually understands or what it sees about the world. You have to remember that a ventilator is a very sophisticated but kind of stupid fundamentally machine, in that it's just a computer with tubes going into it and tubes coming out of it, right? So the only understanding it has of the world outside itself is the pressure inside those tubes and the flow that's going through those tubes. So looking at these curves is like looking into what the ventilator actually sees of the outside world, right? So if you have any ventilator problems, one of the most important things is to look at these curves to understand the ventilator's perspective of what's going on. On the PB840, the whole respiratory cycle is color-coded so that inspiration is in green and expiration is in yellow. And also by convention, inspiratory flow, or I should say more precisely, flow that goes into the patient is positive, and flow that comes out of the patient is negative. So at least for this particular ventilator patient interaction that we're looking at here, this is just an example on this screen. Pressure when it's positive is pushing flow into the patient during inspiration, during the green part of the curve, and then during expiration, the yellow part of the curve, the pressure goes back down to where PEEP is set and flow comes out of the patient. And that's why it's negative here. So the ventilator sees pressure and flow and monitors pressure and flow over time in the inspiratory and expiratory tubing. So we know how the ventilator sort of looks at the outside world. Next question is, how does a ventilator think about a ventilatory cycle? How does it break up a ventilatory cycle? And the answer is into 4 phases. 2 of the phases are pretty easy to remember. They're self-explanatory. That's expiration and inspiration. And if you can remember those 2, you can remember the other 2 are expiration to inspiration and inspiration to expiration. These are the 4 phases. This is how a ventilator thinks about the ventilatory cycle. This is the anatomy of the ventilatory cycle. And expiration and inspiration are kind of like periods during which the ventilator has a job to do, while expiration to inspiration and inspiration to expiration are the transitions between the ventilator's kind of different jobs. Each one of these phases has a phase variable that either says when it happens or what should be happening during that phase. During expiration, the phase variable is the baseline, and that's just the baseline pressure that the ventilator maintains when it's not providing the inspiratory pressure, or another way to put it, PEEP. Expiration to inspiration is called the trigger, and that's the timing of when inspiration should start. During inspiration, this is basically the description of what the ventilator's job is, or what inspiration should look like, and that's called the target. And inspiration to expiration is the end of inspiration, and it's called the cycle. One way to put it is that you cycle off back to your baseline, or that ends the cycle. Starting in expiration, the phase variable is the baseline, and that's PEEP. Basically, it's a pressure, a baseline pressure, that you're going to build each breath off of. So between each inspiration, you go back to this baseline, and during inspiration, you provide a pressure on top of the baseline to sort of create the flow for each breath. All that the vent does during this period is it maintains PEEP, either by opening or closing valves just to maintain pressure inside the circuit during end expiration, and it waits. It's waiting for a signal to start the next breath. On the interface here, the baseline phase variable is selected here, where you set the PEEP. So setting PEEP is setting your baseline pressure, and you can see it, the actual output baseline phase variable up here. So we set it to 5.0, machines aren't perfect, so it came out to 5.1. And then on the graph of the pressure and time curve, you can see that the baseline PEEP is this dotted line here. So what is the vent actually waiting for during the baseline? It's waiting for a signal to start the next breath, and that is the trigger. The trigger is the expiration to inspiration phase variable, and it dictates when inspiration starts. There are 2 types of triggers, 2 broad types. There's a vent trigger, also called a time trigger, or a patient trigger. The analogy I like to use is that if you're a ventilator and your job is to provide inspiration, then you have to know when it's time to go to work, right? So if during your workday you provide inspiration, if you use an alarm clock to wake you up in the morning to go to work, that's a vent trigger. That's a time trigger. If your boss calls you at home and says it's time to come into work, that would be more like a patient trigger. In one case, you're just waiting a certain amount of time to say this is when the next breath is going to start. In the other case, you get some signal from the patient to say this is when the breath should start. So vent trigger, you're just waiting a certain amount of time. Patient trigger, you get an actual signal from the patient, either a change in pressure or flow in the tubing because the patient made an effort, and that starts inspiration. Within patient trigger, there are two different types of signals that you could monitor for, either a flow through the tubing or a pressure through the tubing. Both of those are patient triggers. They're just different methods of detecting when the patient is trying to take a breath in. So the trigger is what starts inspiration, and that goes back to this fundamental question of who gets to control breath timing. The trigger defines whether the patient says it's time to breathe in, and that's a patient trigger, or whether the vent says it's time to breathe in the setting of a vent trigger or time trigger. So if you completely set it to only time triggers, that's giving the CPU complete control, whereas if you set it to only patient triggers, that's giving the patient complete control over when the breath starts. On the other hand, if you use an assist control mode, that's using a combination of both. What it does is it monitors for patient efforts with a patient trigger, and then it has a backup rate set by the CPU, which is a time trigger. On the PB840, you can identify whether each breath was time triggered, or triggered by the ventilator, or patient triggered by a signal from the patient. And that's by looking at the letter in the upper left-hand corner of the screen. If you see a C, that is a vent-triggered breath, and it's a C because it means control. For historical reasons, the terms are kind of confusing, but just remember that a C means a control breath, which was a vent-triggered breath. The ventilator started that breath. And if you see a C, that means the most recent breath was vent-triggered. On the other hand, if the ventilator gets a signal from the patient to start a breath and it uses that signal to start the breath, that is a patient-triggered breath, and what that gives you is an A for assist. It's not a great term because all breaths in mechanical ventilation are assisted, so it doesn't make sense to say that control breaths aren't assisted and assist breaths are assisted. It's just the term we have to deal with because it's the one that's in the system. But it's more accurate to say that if you see an A, which stands for assist, that means that that breath was triggered by the patient. For this example here, for these two examples, the control breath, that first breath we saw, you see that there doesn't look like there was any effort by the patient because the pressure inside the tubing didn't drop. Whereas for this breath, you see this negative pressure deflection, and maybe that negative pressure deflection was enough to trigger either the flow or the pressure sensor in the ventilator to say the patient's trying to breathe in, let's start the breath. In real life, it's not often this obvious that the patient has tried to take a breath in, so I usually rely on just looking at the letter. If I see an A, it was patient triggered. If I see a C, vent triggered. So where do you set the trigger down here at these blue buttons, and where is the actual output of the trigger? It turns out it's not as straightforward as the baseline, which is PEEP, which you just set 5 here. You don't set a time trigger. What you set is a respiratory rate or frequency. This little F here means frequency, 20 breaths a minute. That would be your breathing frequency or your respiratory rate. And this translates into a time trigger inside the ventilator's CPU. So at 20 breaths a minute, if there are 60 seconds in each minute, that means in 60 seconds you have to give 20 breaths, so 60 over 20 is 3. So what the ventilator is actually going to do is between each breath, between the start of each breath, it's going to count to 3 seconds. 1 Mississippi, 2 Mississippi, 3 Mississippi, and if nothing else happens, if it doesn't get a patient trigger in that amount of time, then it's going to give a time trigger. So that's the set respiratory rate. That gives you your time trigger. The patient trigger is set right here at this V sends, and what this actually means, a V with a dot on it, the V is volume, and putting a dot on something just means over time. So volume over time is flow, so this is a flow sensitivity trigger, meaning that if the patient generates 3 liters per minute of inspiratory flow during the baseline period, the ventilator is going to interpret that as the patient trying to breathe in and will start the breath, and that will be a patient-triggered breath. So this is the set patient trigger. The actual outputs of the triggers are up here at the top. The first we talked about in the previous slide, this is the actual trigger for the current breath. This shows that the most recent breath was an assist breath, meaning it was patient-triggered. So for the most recent breath, There must have been at least 3 liters a minute of inspiratory flow that the ventilator interpreted as the patient trying to take a breath, triggered the breath. I can tell that for this example, none of the breaths are actually time triggered. They're all going to be patient triggered, and that's because the actual respiratory rate is higher than the set respiratory rate. We call the set respiratory rate sometimes a backup rate, and it's the minimum respiratory rate that the patient's going to breathe on these settings. And that's because there's the time trigger there, and if there is no patient trigger, that is, the patient's not making any efforts, then the patient will breathe at this 20. However, if the patient is making respiratory efforts and those efforts occur more often than 20 times a minute, you will not have any time-triggered breaths. They will all be triggered by the patient. So if you turn this down to 15 breaths a minute, it won't do anything. The patient will continue to breathe at 22 breaths per minute because they're currently breathing with all patient-triggered breaths. There are no time-triggered breaths, so lengthening the time trigger will have the effect of the ventilator just waiting longer, but since it's already getting input from the patient that are triggering patient-triggered breaths, they'll continue to breathe at 22 breaths a minute. On the other hand, if you turn the respiratory rate up to 35 breaths a minute, say, then the patient's going to breathe at 35 breaths a minute, and every breath will be time-triggered because that time trigger is so short that it's going to go off before the patient gives any kind of signal that they want to breathe in. And on top of that, breathing at that rate is probably going to make the patient hypocapnic. It's just much higher than their neural respiratory rate. One last point on all of this. We're in an era right now where we're trying to save diaphragms. There's this principle that if the patient is trying to breathe in really hard because you're not giving them enough support, then they actually injure their diaphragm from sort of an overexertion, stretching, trauma to the diaphragm itself. On the other side, if you're giving the patient too much respiratory support, too much ventilatory support, and they are not making any of their own efforts because you're essentially over-breathing them, then the diaphragm is kind of like a use it or lose it muscle. If they're not using the diaphragm at all, the diaphragm atrophies. So we don't want that either. So the point is that if you go to the bedside and you see just C, that is, breath after breath is triggered by the ventilator, either that patient is paralyzed and you want them to be paralyzed, so they shouldn't be triggering, or you were over-breathing them and making them hypocapnic and going way beyond their neural respiratory drive so that they're not using their diaphragm at all, and you're at risk of atrophying their diaphragm, and then it's going to be harder to get them off the ventilator. In that case, I would say turning down the set respiratory rate is probably the right thing to do to make sure the patient makes some efforts. On the other hand, if every breath is patient-triggered, that doesn't necessarily mean that they're trying too hard. Seeing whether or not a patient is really taking really big efforts is something I think we'll get to later in this lecture. We come now to the target, which is one of the less intuitive phase variables, but it's pretty simple. If I say that the ventilator's job is to provide inspiration, the target could be thought of as the ventilator's job description. The target describes what the ventilator actually tries to do during inspiration, and that means it determines what the inspiration actually looks like. That is, the shape of the flow curve or the shape of the pressure curve. The target has nothing to do with the timing of inspiration, that is, when inspiration starts. Remember, that's the trigger, so the trigger starts inspiration, but doesn't tell you what you're supposed to do in inspiration, just like the target is what you actually are supposed to be doing during inspiration, but doesn't tell you when inspiration starts. And I'm going to jump ahead a little bit and just say that the cycle is the thing that ends inspiration and also has nothing to do with the target. Think of it like this. You probably have some friends who are lawyers, while you yourself, if you're listening to this, presumably work in healthcare. Both you and your lawyer friend might use an alarm clock to wake up in the morning so that you go to work. That would be your trigger to start your workday. What you do at work, though, is completely different, even if you use the same thing to tell you it's time to go to work. So the trigger really has nothing to do with the target. It just says when inspiration starts. It doesn't tell you anything about what actually happens during inspiration. The cycle is sort of the same thing. The cycle tells you when the workday is over. Lawyers have something that tells them the workday is over, just like doctors have something that tells them the workday is over, even though they have very different jobs during the workday itself. So don't get confused about assist control. Saying assist control is describing the trigger. Assist control means there is a patient trigger and a timing trigger, but it says nothing about what actually happens during inspiration. What actually happens during inspiration is described by the target. The target can either be flow or pressure. On this side, here are two examples of flow targeting, and over here is an example of pressure targeting. In the flow targeting, I have a square wave here and a decelerating ramp, or just ramp wave shape here. For the square wave, it's pretty simple. Say you're down here at baseline, so there's no flow in or out of the patient because we're at end expiration, waiting, 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 and then something triggers inspiration, either a time trigger or patient trigger. So now it's time to give inspiratory flow, and since we're in a square wave form, what we're going to do is go up to, say, 60 liters a minute. Just keep it at 60 liters a minute, 60, 60, 60, 60, 60, cycle off, inspiration is over, back to baseline. Okay, that's a square waveform. So here with the ramp waveform, we're at end expiration, there's no flow in or out of the patient, something triggers the breath, so trigger, start inspiration, and you start at this peak value, say again 60 liters per minute, but it really could be anything, but 60 liters per minute, and then you decelerate, that is, you in a linear fashion slowly decrease how much flow you're giving into the patient. So 60, 50, 40, 30, 20, and then 0, cycle off, and so inspiration is over, and you go back to your baseline. Between these two, you can try to replicate this breathing shape. So try to breathe like you're breathing in a square flow shape. It's like, so it would be like a really quick breath in, quick short breath in, where you maintain the same flow throughout inspiration. That's not really how people breathe. That's not very physiologic, and it's pretty uncomfortable. So I don't really find a lot of uses in clinical practice for the square wave shape. Now, if you just take a relaxed, deep breath in, you find that at the beginning of the breath, you breathe in real fast, and then you sort of naturally just decrease how fast you're breathing in. So by the end of the breath, your inspiratory flow is very low. So this is more physiologic and more comfortable for patients in clinical practice. So I tend to almost always use the ramp waveform when I'm flow targeting. Now on the other side is a pressure targeted mode. And in pressure targeting, the way it works is the ventilator tries to reach and maintain a pressure throughout inspiration. So it's more like a square. There is no real ramp waveform in pressure targeting. It's really just a square wave shape. So how does that actually work? How does a vent reach and maintain a pressure target throughout inspiration? The easiest way for me to think about this is to think of the ventilator as a flow generator, a machine that can give flow. It's not necessarily a machine that makes pressure, but it gives flow into the patient, and it can measure the pressure as the result of giving that flow. So if a ventilator has a pressure target, what it does is at the beginning of the breath, it gives a big inspiratory flow in order to reach that pressure target. So it pushes a bunch of air into the patient and then measures the pressure in the tube as a result of giving that flow into the patient, right? As inspiration goes on, in order to maintain its pressure target, it has to readjust how much flow it's giving. In this case, the patient is paralyzed, so just naturally what's going to happen, the only way to maintain a constant level of pressure throughout inspiration is by giving a flow shape that is decelerating, and that has to do with the mechanics of the patient's lung and chest wall, that as you give more and more volume into the patient, you have to provide less and less flow if you want to maintain a constant airway pressure. If the patient were to try to take a big deep breath in the middle of inspiration, what would happen is that the pressure in the tube would drop, right? So if you suck on a tube, the pressure in the tube would drop. But the ventilator doesn't want that to happen, so it would have to give more flow than this decelerating shape. It would have to increase the flow in order to maintain the pressure target. That's what machines are good at. Machines are good at doing something, measuring the results, and making minute changes in a feedback mechanism. And that's how pressure targeting works. The ventilator provides a flow into the patient, measures the resultant pressure, and then changes the flow on the basis of how far off the pressure is from the pressure target. Let's look at some examples of what the pressure time and flow time curves might look like depending on the target. So if we are in a flow targeted mode, flow should look the same for every breath because this shape is the ventilator's job description, and this is what it should do for every inspiration. So if this is what the pressure curve looks like on this breath, let's just assume the patient was relatively relaxed throughout this inspiration, and this is the resultant pressure curve. If the patient tries to take a deep breath in the middle of inspiration, what is the flow curve going to look like, and what is the pressure curve going to look like? So if the patient tries to take a big deep breath in, the flow curve should look the same. Remember, I said this was flow targeted, and this is the ventilator's job. It's supposed to reproduce this shape with every inspiration. So this is a little bit idealized, but what should happen is the flow curve should look exactly the same. So what's the pressure curve going to look like? One of the things I like to say is that if you are in a flow targeted mode, it's like flow should always look the same, pressure be damned, or pressure can look like whatever it's going to look like. On the other hand, if you're in a pressure targeted mode, pressure should always look the same, and flow be damned. Flow is going to look like whatever it's going to look like. So in this case, the flow curve is the same because you're in a flow targeted mode. The pressure curve will look like this if the patient tried to take a big deep breath in, right? So what happened here is the patient sucked on the tube, and in order to maintain the flow shape the same, the ventilator actually had to increase the resistance by like shutting off one of the inspiratory valves in order to keep the patient from breathing in any faster than this, right? Remember I said that I'd say a little bit about how you could tell if a patient was trying to breathe too hard or if you weren't providing enough support even though you see A on the trigger. Well, this is one of those situations. Right here, the patient is trying to breathe in much harder than this flow curve is allowing. The ventilator is not letting the patient breathe in any faster, and as a result, the patient is sucking really hard on the tube and dropping the pressure low. If you see this, this is almost like the patient is breathing harder, working harder to breathe than they would be if you just extubated them. Because if they were extubated, they wouldn't be generated a big negative pressure as a result of a flow restriction like this. They would be allowed just by like breathing in the atmosphere to breathe in faster. But this is a case where the ventilator is preventing the patient from breathing in any faster, and as a result, the pressure in the tube drops low. On the other hand, if the patient coughs in the middle of a breath and you're in a flow targeted mode, what are the curves going to look like? Well, again, this is idealized, but if it's a flow targeted mode, the flow curve should look exactly the same. The pressure curve, on the other hand, because now you have the ventilator on one side driving a flow of air into the patient, and the patient on the other side trying to drive flow out of his or her lungs, they're going to collide, those two flows, right? And that's going to create a big high pressure inside the tube. And this can be one of those causes of high peak pressures when you're in a flow targeted mode. The patient could be coughing into the tube, and that will sometimes set the alarm off. A major point here is that flow targeting tends to be more uncomfortable than pressure targeting. And that's because we like being able to change how fast we breathe in or out. If you're sitting and listening to this right now, you may notice that sometimes you take a deep, slow breath like a sigh. Sometimes you take a shorter breath with maybe a lower inspiratory flow. But it's comfortable being able to change how fast you breathe in or out. And flow targeting does not allow you to do that. The ventilator will always want to give the exact same flow in the exact same shape with each breath. And that can be uncomfortable because if you want to cough, the ventilator doesn't care and it will push this flow into you. And if you want to take a bigger, deeper breath, the ventilator doesn't care and it will keep your flow this same level even though you would like a faster flow, and as a result, the pressure in the tube will drop. Let's look at the same scenarios but now in a pressure targeted mode. So if we're in a pressure targeted mode, that means that the pressure curve, the pressure time curve, is always going to look the same, or the ventilator is going to do its best job to always reproduce this pressure curve or maintain pressure at this level throughout inspiration, flow be damned. So if the patient tries to take a big deep breath, what's going to happen? Well, the first thing that's going to happen is the ventilator will notice that the pressure in the tube is starting to fall. So in order to prevent the pressure in the tube from going below the pressure target, the ventilator will provide more flow. So if everything works out exactly as it's supposed to in this idealized example, the pressure curve will look exactly the same, and that's because the ventilator provided a big inspiratory flow to maintain that pressure target when the patient tried to take a big deep breath in. You can imagine that that's a lot more comfortable than the ventilator not caring that the patient wants to breathe in and just limiting inspiratory flow. Instead, in this pressure targeted mode, when the patient tries to take a big deep breath in, the ventilator provides that increase in inspiratory flow that the patient is essentially asking for. What's going to happen if the patient coughs? Well, again, this is idealized, but if we're in a pressure targeted mode, the pressure curve should always look the same with each breath. And since the patient is coughing, in order to maintain the pressure target, the ventilator doesn't really have to provide any flow into the patient and might even have to let some flow out of the patient to keep the pressure from going too high, right? So you get this flow curve that kind of looks like and the pressure target is maintained strictly by the expiratory force that the patient generates when they cough. You can imagine that this is much more comfortable than the flow targeted mode, right? Because if you're the patient, when you tried to take a big deep breath in, the ventilator let you do that. The ventilator provided an inspiratory flow to maintain its pressure target, and it's like you and the ventilator were working together. Same thing with the cough. Instead of the ventilator forcing you to take an inspiratory flow in the middle of a cough and resulting in this huge pressure, the ventilator decreased the flow in order to maintain its pressure target at the same time you were coughing out. So let's talk about the target in specific modes of mechanical ventilation. Let's start with volume assist control. You'll remember that assist control refers to the triggers, the control part meaning that there is a time trigger and the assist part meaning there is a patient trigger. It doesn't tell you anything about the target. If you go to the bedside for a patient who is on volume assist control ventilation, you'll find that the flow curves always look the same. For each breath, the flow time curve should reproduce the same shape over and over again, and that's because volume assist control is a flow targeted mode. The same flow is targeted with each breath, with each inspiration, and the pressure can be virtually anything. The ventilator doesn't care. It does whatever it can to try to maintain that same flow shape with each breath, and pressure could be really low or pressure could be really high. One of the frustrating things about learning about mechanical ventilation is that the nomenclature is all over the place. Though it's called volume assist control, it's actually a flow-targeted ventilatory mode. The volume in the name has more to do with the cycle, and we'll get to that in the next couple slides. Back at the interface here, we can see that the target has two separate components. The first is the set maximum flow. So remember, V with a dot on it is volume over time or flow. So this is maximum flow, and it's set to 60 liters per minute. The maximum flow is the maximum flow that occurs during each inspiration, so it would be the top of this little triangle in the setting of a ramp waveform. The other component is the actual shape of the inspiratory flow curve, and in this case it's a ramp or kind of a triangular shape. If you push this button, you can change it to a square wave. So if you have a patient that you want to have a short inspiratory time, there are kind of two ways to do that. One is to change the shape of the inspiratory flow from a ramp to a square wave, because square waves tend to have a shorter inspiratory time. But the alternative, and what I usually do because it's just more comfortable I think for patients in general, is I will just turn up the Vmax. And if the volume is the same for each breath, then turning up the highest point on this triangle will make the triangle not as wide, because the area under the curve will remain the same, and that means that the base of the triangle has to shrink. Up here on the actual flow time curve itself, you can see that for each breath, the actual maximum flow is the same. This is a flow targeted mode, so it should be the same for each breath. And the shape of each inspiratory flow curve is the same for each breath. Let's move now to pressure assist control and pressure support modes. What is the target in both of those modes? If you have a patient who's making inspiratory efforts, a patient who isn't paralyzed, you'll notice that for virtually every breath in one of these modes, the pressure wave, the pressure curve is going to look the same, and the flow curve could be anything depending on whether the patient's making an inspiratory effort or coughing. And that's because these are pressure targeted modes. The ventilator does the best job it can maintaining pressure throughout inspiration at this set level, and it does that by altering flow to whatever is needed in order to maintain that pressure. I said earlier that the nomenclature can be frustrating and confusing, and this is a good example of that because for pressure assist control and pressure support, the word pressure describes the target. These are pressure targeted modes. Whereas for volume assist control, the word volume doesn't describe the target, it actually describes the cycle. There's no such thing as a volume targeted mode. You're either flow targeted or pressure targeted. Those are the only two types of targets. Volume just describes the cycle. The names of the modes are confusing, but we just kind of have to deal with it because that's the nomenclature that the manufacturers use for historical reasons. But if you really know what you're talking about, you will say something like volume assist control is a flow targeted mode, or pressure assist control is a pressure targeted mode, or pressure support ventilation is a pressure targeted mode. And if you say that, then I know you know how the ventilator is working during inspiration. On the interface, setting the target in pressure assist control is pretty simple. It's just set inspiratory pressure. And this set inspiratory pressure is given on top of PEEP. So on the interface, setting the target in pressure assist control, the pressure target is pretty simple. It's just the set inspiratory pressure. And this pressure is given on top of PEEP, so 5 of PEEP is the baseline in this setting. That's 5 of PEEP right here. The inspiratory pressure is given on top of that, and that spits out the peak pressure, right? So 5 plus 20 is 25. That would be this top line here, should be about 25. And the most recent reading for the actual measured peak pressure is 26, pretty close to 25. We've gone through 3 of the 4 phase variables, and we come now to the cycle, the last phase variable. This is the one that tells the ventilator that inspiration is over. It's something that when it is reached, tells the ventilator to stop giving flow or stop giving pressure and let the patient breathe out, stop inspiration. The cycle can be volume, time, or flow. If it's volume, what that means is while the ventilator is giving inspiration, it's measuring how much volume has gone into the patient. Another way to say that is the area under the flow time curve, because flow times time is volume. Once the ventilator has given the set volume for the cycle, it ends inspiration or cycles off and goes back to baseline. If the cycle is time, that means that the ventilator starts inspiration, and as it's giving inspiration, it is measuring how much time has gone by, and once the amount of time that has been set as the cycle has gone by, it stops inspiration, and that would be a time-cycled breath. A flow-cycled breath would be one in which the ventilator says, at the beginning of inspiration, the flow that is given is this big. As flow diminishes through inspiration, as soon as flow gets below some threshold, I'm going to stop the breath, and that would be a flow-cycled breath. So again, the cycle is the thing that tells the ventilator that inspiration is over and it's time to end inspiration, and it can be the amount of volume that has gone into the patient, the amount of time that has passed since the start of inspiration, or it can be a flow threshold that when reached tells the ventilator stop giving the inspiratory flow. Remember I said that in volume assist control, volume does not describe the target, it is a flow targeted mode. Rather, volume describes the cycle. This is a flow targeted volume cycled mode, meaning a certain amount of volume once given into the patient ends inspiration. In this case here, we've set a tidal volume of 500 milliliters. That means that as the ventilator gives inspiration, it measures how much has gone into the patient, and as soon as it has given 500 milliliters, it stops inspiration. And you can see here that the delivered tidal volumes are the area under the curve for each one of these inspiratory flow curves. What is given at the top is actually the measured expired tidal volume. And the expired tidal volume and the delivered tidal volume can sometimes be discrepant. In this case, we got 19 extra cc's. That could just be noise, but it could also be that the patient breathed out a little bit after inspiration had been delivered and they had some extra volume or something, they breathed it out. It could be that a nebulizer is attached to the tubing and delivering some flow, or it could be that there is a leak somewhere that allowed some extra volume to get into the patient during inspiration. There are a lot of different reasons that the set tidal volume and the measured expired tidal volume can be discrepant, and you kind of have to address those possibilities when you see this happening. 19 milliliters is not really something I would worry about very much. When this is set at 500 and you get volumes of like 600, 700, 800, then I have to figure out why that's happening. Moving now to this cycle in pressure assist control, it's a time-cycled mode, meaning that the elapsed time is what stops inspiration or defines the end of inspiration. That is, the ventilator starts inspiration after it is triggered. It counts the time that's been going by, so 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, whatever. And as soon as the elapsed time that is set has passed, it stops inspiration. That ends inspiration, and the ventilator cycles off back to baseline. You can see on the interface here that there is an inspiratory time setting right here. This is the set inspiratory time. This is the number of seconds that the ventilator will maintain the inspiratory pressure or the target before it ends inspiration. And you can see that here. Each inspiration has a certain length, so the actual inspiratory time should be the same for each inspiration since it's set at 1 second. So for each breath, it will make inspiration last for a second. And you can adjust the inspiratory time depending on what you want the I to E ratio to be. If you want the patient to have more time to expire, you might decrease the inspiratory time. You just have to be careful that you're allowing enough volume to get into the patient to make sure they're maintaining ventilation. So the cycle in volume assist control is volume, and the patient is going to get the same volume with each breath because it's the same setting with each breath. You set the tidal volume, and that's the volume the patient gets with each breath. In pressure assist control ventilation, the cycle is time. So inspiration will always last the same amount of time. This is important because in both modes, in both volume assist control and pressure assist control ventilation, the patient does not have control over when inspiration stops. Because it is an assist control mode and there is a patient trigger that's implied by assist, the patient has control over when to start each inspiration. They can just suck on the tube and the ventilator will deliver inspiration. But once inspiration has started, the patient has no control over how long inspiration lasts. And that could be uncomfortable. I mean, think about it. You're breathing in, and if you wanted to take a big long sigh and you could only get a certain amount of volume, it would be uncomfortable to suddenly have the breath end while you're in the middle of it. Or if the breath is only going to last a short time and you want it to last longer, that could be uncomfortable. Or say the breath is going to last a long time, but you want to cough in the middle of the breath and it's still pushing air into you, that could be uncomfortable. Pressure support ventilation is special compared with the volume assist control and pressure assist control in that the patient has control over how long the breath lasts or how long inspiration lasts. And that's because pressure support ventilation is a flow cycled mode. And this is a little complicated. It's harder to understand than volume cycling and time cycling, but it works like this. At the beginning of the breath, the ventilator measures the peak flow. And then as the flow naturally decays during the breath, because flow will naturally decay if you're trying to maintain the same pressure throughout the breath, and once it reaches a certain threshold of the peak flow, usually 25%, it stops the breath, and that's flow cycling. So the ventilator measures the peak flow at the beginning of the breath, and then once the flow decays to some threshold level of that initial peak flow, it stops the breath. And as you can see here, this first breath has a low initial peak flow, and it's rather long, like the patient just took a kind of weak breath, but it lasted a long time. And that's because the flow decayed rather slowly, so it has a long inspiratory time. On the other hand, this breath is much shorter. It has a higher peak flow, but the flow decays much more rapidly, maybe because the patient didn't want to breathe in quite as long and tried to breathe out in the middle of the breath. I'm not sure. But the point is that the inspiratory time, as well as the inspiratory volume, the volume given with each breath, can vary. That's what's special about pressure support ventilation. It is probably often the more comfortable mode between volume assist control and pressure assist control, because the patient has control over when the breath starts, how big the breath is, and when the breath ends. Just think about what you would want if you were intubated and mechanically ventilated. If I were mechanically ventilated, I would want to be on a pressure support mode. So this is the mode I would prefer to use if possible, as long as the patient's condition allowed it. Like, they can't be paralyzed, and this is probably not the easiest mode to use in something like ARDS, where you really have to protect and monitor lung volumes. But certainly for the patient who was intubated just for a procedure, or maybe even intubated for airway protection, pressure support ventilation is a pretty good mode. On the ventilator interface, the flow cycle sensitivity is this eSends button, and right here it's set at 25%, and that means that for each one of these inspiratory phases, the peak flow at the start of inspiration was measured at 100%, and as flow decayed below 25% of that initial peak flow, the inspiratory phase was ended and the ventilator cycled off back to baseline. I think one of the earliest troubleshooting problems that people learn about when they're learning about mechanical ventilation is the high pressure alarm. And that's when, if you have the pressure time curve here, there is a high peak pressure. That is, the highest pressure during inspiration is beyond whatever the alarm threshold is. If there is a high peak pressure, it's coming from one of two places. It's coming from the airways, which consists of the tubing between the patient and the ventilator, the endotracheal tube, and the patient's airway itself, which is everything from the end of the trachea with the endotracheal tube in it all the way down to the main stem carina and the small airways all the way out until you get to the respiratory bronchioles. Sometimes the cause of a high pressure due to increased airway resistance is obvious, like if somebody has somehow crimped the tubing by rolling it under a wheel or squeezing it against something. That will cause a high resistance in the tubing, which will cause a high airway pressure, and you can fix that right away, but you have to look to notice it. Sometimes it's less obvious, and it could be mucus that is stuck in the endotracheal tube. It could be a mucus plug in the patient's airway itself. It could be from bronchoconstriction in the case of asthma, or from a COPD exacerbation. The other reason you could have a high peak pressure is because there is low lungs and or chest wall compliance. That is, the lungs and the chest wall are stiff. Something obvious that could do that is if somebody comes up and just sits on the patient's chest, that will cause very low compliance and the high peak pressure alarm will go off. Even the expiratory muscles of the patient can cause a high peak pressure, of course, because if the patient's coughing, they're going to be coughing airflow up into the tubes here, and if you're in volume control and it's pushing air at the same time, that's going to cause high peak pressures. I'm just harping on this to point out that you don't immediately need to run to the ventilator and start pushing buttons. You can often tell why there is a high peak pressure just from looking at the patient and looking at the ventilator. Okay, so you've examined the patient, you've examined the ventilator, examined the tubing between them, everything looks okay. What's the next step? This is when you push the inspiratory hold button or the inspiratory pause button. What that does is it stops all flow moving through the airways. And if there's no flow moving through the airways, then there's no pressure generated by the airways, because the pressure that comes from the airways is from flow, from air molecules actually colliding with the walls of the airways. So all the pressure that's left over when you do an inspiratory pause is from the lungs and the chest wall and whatever's outside them and potentially compressing on them. So if we do our inspiratory pause and it looks like this, this breaks up our peak pressure here into the airway component and to the lungs and chest wall component. And in this example, this is a high peak with a normal plateau pressure. Since this is a normal plateau pressure, you know the source of the high peak pressure is from the airways. Alternatively, if you do your inspiratory pause and it looks more like this, then the pressure that's from the airways is obviously very small. It's just this, and most of the high pressure is coming from a high plateau pressure, which means that the source of the high peak pressure is something to do with the decreased compliance or increased stiffness of the lungs and chest wall. This is the curve you would see in something like asthma or a mucus plug or COPD. And this is the curve you would see in something like ARDS or obesity, sometimes pregnancy, ascites, anything that makes it tougher to fill the lungs and chest wall with volume. And that brings us to the end of this lecture on mechanical ventilation. Please let me know if you have any comments, any criticisms. I'd be very happy to hear it. And until next time, I'm Tom Tolbert. Thanks a lot for watching.